Hello everyone, welcome to module 11. In this module, we are going to learn why we should use position tolerance instead of linear tolerance to specify the position. Let's look at one of the join. This join we have learned before. If we use the plus minus tolerance to specify the position from the upper surface to the bottom surface, so what's going to happen? The problem is we don't know how to measure that, and we learned that in the previous module, right? We don't know to measure this position or distance, which side to be used as a datum. Short side as datum or longer side as a datum, we don't know. So if you use different side as a datum to measure this distance, you will get different result. So this join we suppose to change to the profile as we mentioned. Okay, so let's look at another way when we use the plus minus to define the position of a hole. What will be happening here? Okay, let's look at here. First, as we know, this kind of join is pretty common, pretty common, but there's so many problems inside. First problem, datum is not clear as we mentioned for the plus minus to specify the position of the profile. You see here, have same problem. So we know when we use plus minus, we don't know which side supposed to be the datum used to be first. As we know here, this one is the datum, is implied datum because both dimension is started from this side. So here is implied datum. Same here, this side is implied datum. Okay, so we know this is datum implied, this is datum implied. But the problem is we produce the part. This side and this side is not 90 degree. There's always error. The product is not perfect. We know that. Okay, so the problem is how to locate this component. Number one, you can push this side against gauge or the marble table, and then you push this side to this surface. You can imagine there's a gauge here. This is a gauge surface. You push against this side first, and then this number one you push to here, number two you push to here, and then you measure the center of this hole to the surface. This is number one method. Okay, and you have the number two method here. The number two method here, you're going to push this to this side. So you're going to use this as a first datum. Okay, and then you're going to push this component to here. That means you're going to use this side as the second datum. And then you're going to measure the actual hole center to the surface. So you may know that because the thickness of this component, this and this one is different. Let's give it very extreme component, then we understand better. How about this one? If the component is like this one, then obviously if we use this side to locate the part, then this part will be tilted like that, right? Like that. And this hole obviously will be different to locate this first and locate this second. So this one, the measurement of the position will be total different result because you see here from here to here obviously is different from here to here, right? So the question here is which one is correct? So this one is correct or this one is correct? There's no answer. You cannot find answer. Okay, so whose fault? Now we have two results. And one result said this position is good, another said this distance is not good. Okay, so you know the answer, right? The answer is design engineer. The design engineer produced incorrect join. They shouldn't use the plus minus to specify the position of the hole. Okay, so what we need to do here is we need to change this join to position, as you can imagine, right? Because the total cost, I just keep saying, use the position tolerance, use the profile tolerance. Okay, once you use the position tolerance here, then the datum sequence has been defined. The first datum A is the bottom surface, datum B is this surface, and datum C is this surface. And you know here this first one is A, the second one is B, the last one is C. So you will know how to locate the part. First you push against A, and then you push against B. The last one you push against C. So the sequence is clear. There's no second way to locate the part. So that means the understanding is clear, it's unique. For this join, the understanding is ambiguous. Okay, you cannot measure it properly. Alright, so this is the I'm saying here. Once you define the sequence in the position tolerance, then the measurement will be unique. There's only one way to measure this part. Okay, now we talk about second problem to use the plus minus. The second problem is the tolerance zone. It doesn't make sense. Let me show you here. Look at this plus minus 0.2. That means from here to here is plus minus 2. And here is plus minus 2. That means the center is supposed to be deviated from here plus minus 0.2. That means the tolerance zone is a square. You see here it's a square. And the center is required to within this square zone. That's the requirements from design engineer. Okay, but the worst deviation actually is the corner here, or here, or here, or here. But it is still within the tolerance. However, this deviation is not plus minus 0.2 anymore. From here to here is plus minus 0.28, and it's easily to calculate out. Here is 0.2 and here is 0.2, and you can get the diagonal distance easily, right? It's here plus this one, and then you get this one. Alright, then this one is this one. Okay, so the worst distance will be plus minus 0.28. So in other words, this plus minus 0.2 is allowed deviation actually is plus minus 0.28, or is something like that. If we use the position tolerance 0.56, then you get same, at least the worst deviation will be the same, plus minus 0.28. I mean the worst situation. Okay, however, this one have more area than this one. So what does it mean, more area? Let's give you one example here. From function point of view, function, I mean for hole, the assembly will be mating with a shaft. So in that case, if you are allowed to deviate in this direction plus minus 0.28, that means any direction supposed to be same deviation, right? Because the hole and the shaft has the gap evenly all around. So that means any direction you're supposed to give the same deviation, right? So put that way, if the parts falling into here, if the center falls to here, this area, the function is okay. No problem, the function is okay. However, it's outside of this squared tolerance. So what does it mean? The function is okay, but it's outside of tolerance. So that means there's waste. There's waste there. Okay, so this portion actually function is okay, but because it's out of the tolerance of the square tolerance zone, then you're going to get rid of it. So it's kind of waste. Okay, it's kind of waste. So you can see here, if you convert it to position tolerance, as we mentioned here, then this position tolerance has 57 more area than square tolerance zone. But both of them, they have the same worst deviation. As you mentioned, the worst deviation for this one is plus minus 0.28. The worst deviation for this position is plus minus 0.28. Okay, but the qualified part, this one has more. So we notice the second issue for the plus minus tolerance to specify the position is the tolerance zone is not make sense. Okay, it's not make sense. Okay, then we are going to talk about the last one here, the drawback, the problem of plus minus. The plus minus, when we use plus minus to specify multiple holes like this number one, this number two holes, and then you're going to have accumulation of the tolerance. For example, here 15 plus minus 0.2, 20 plus minus 0.2, and the total from here to here will be 35 plus minus 0.4. That's accumulation. Okay, just imagine you have more 6, 7, 8, 9 holes, then the accumulated tolerance will be big. Okay, so what about the position? So if you look at the position tolerance 2 times and reference to ABC, what does it mean? 2 times position reference to ABC. That means both holes, they are using the same datum ABC. Even they put basic dimension 15, 20 here, but this hole still use the datum ABC, and this hole still use the datum ABC. Right? So in that case, there's no tolerance accumulation. So even from here to here, the tolerance still 35 plus minus 0.2. There's no accumulation. Okay, so the benefit to use the position is we can get rid of the tolerance accumulation, especially for the pattern of the holes. Okay, all right. So far we have learned a lot about why we shouldn't use the plus minus to specify the position, right? We should use either position or profile to specify the position. So here is the summary. Okay, the benefit here. Okay, so linear tolerance, there's no datum, right? And the understanding is not unique. And the tolerance zone does not make sense. It's square, right? And then the some usable parts will be rejected. Okay, so the function cannot be transmit properly. So this is not recommended to use. Another one here is position, right? If you have datum, we have datum sequence. The understanding is unique. And also the tolerance zone is circular, has more qualified parts. And also we are allowed to add MMC modifier, AOMC modifier, and this we are going to increase the position and give you more qualified paths, reduce the cost. So you can see this module about MMC modifier in the next few modules. You can find it in this course. Okay. Alright, so you may ask, so in which situation we are allowed to use plus minus dimension? Yeah, it tells you something here. When for size you are allowed to use plus minus. For example, it's a pin, and this pin we put 5 plus minus 0.1, and this is allowed. And there's no problem for understanding, because this plus minus is, when we talk about measurement, is use caliper 2 point plus the rule number 1 requirement. Okay, you do not need the datum to measure the diameter, right? You just use caliper. There's no need datum. Okay, the understanding is unique. Okay, for the rest of, for example, the radius, okay, chamfer, and also for the locating parts, angular form, all of this, we shouldn't use the plus minus. But here is called not recommended for chamfer and radius. Let me show you one example here. The radius is widely used plus minus method. However, it's not recommended. Similarly here, the angular is not recommended. Let me explain this one quickly. Why we shouldn't use plus minus to specify the radius. One example here, because it's not easy to measure. Why? Give me one example here. This is the radius plus minus 0.2. And then we need to measure the radius. And as we know, in order to measure the radius, we need to touch point on the surface on the actual part. For example, this is the actual radius here. It's not perfect. Then we're going to touch a lot of point. And then we associate, or we construct a circle. Then we get diameter. And then we get what? We get radius, the actual radius. So you may notice the process is like this way. First, you touch the point. Second, you construct a big circle, and then you get center. Then you get what? You get radius. It looks like perfect. However, there's a big problem inside. Why? Because the physical portion is too small. The physical portion is too small, then it's not stable to use this portion to construct a big circle. Each time when you construct a circle, you may get different circle. For example, first time you may get this circle, and then you touch point again, you measure again, then you get this circle. And each time you will get different result, because this portion is too small. So usually we can say, in order to get a circle from radius, usually we would recommend more than half a circle. Then you touch the point, then you can get a full circle. I would say more than half. Okay, so that's the reason we do not recommend to use the plus minus radius specifications. That's not recommended because of the measurement is not stable. Okay, and then how can we do that? You're going to use the profile. Once you use the profile, then the measurement will be like that. You just touch point, and then you are going to use this point to compare with the CAD model. You do not need to find a big circle. No, you do not need. You just touch this point, you get the actual surface. And then next, you're going to compare with the CAD model. And then you get worst deviation for this profile, because the profile tolerance zone is inner and outer boundary, and it's even, right? This is inner outer boundary. So you do not need to use those kind of point to construct a big circle. There's no need. Okay, so it's going to remove the measurement problem. Okay, so that's why we recommend use the profile, and do not recommend to use a plus minus. Okay, I think that's it for this module. Hopefully you can learn this knowledge and try to, avoid some misleading practice that you used before, and try to use the geometric tolerance, especially the position and the profile. Okay, see you in the next module then.